will start with a review of neighborhood methods. So the basic idea of neighborhood is you are defined by the company you keep in a very simple terms. So if you want to know what is the value for regression, what is the value at a point in feature space, you just need to find neighboring points, actual data instances, which are in the neighborhood of that point. And in a sense, in the simplest term, take the average of them. Right? When you take the average of them, that is called a k nearest neighbors. You're picking k of the neighbors. Now, how many neighbors you pick determines the bias variance trade-off, which we'll see in a subsequent lab, not today. In the bias variance trade-off, what it means is if you take k is equal to 1 and you're only listening to your nearest neighbor, then what happens is, if so happens that that nearest neighbor it has a huge error or it has noise because of whatever reason, it happens to be on the wrong side, you will end up misclassifying your points much more. So the decision boundary is far more complex. On the other hand, so as you increase k, the decision boundary begins to smoothen out, as you will see. And beyond a certain point of smoothing out, now you start developing variance errors. In other words, not bias errors, because what happens is, for example, in the limit of taking all points, k is equal to the number of data instances, there will always be one answer. Y will, in regression, be just it is essentially the null hypothesis. It is the average of all the Y values in the data set. Right? There's no relationship between the X and Y, the predictors and the Y target variable. Likewise, in classification, whichever is the majority class, that class will overwhelm, and all of your predictions will say that every point in the feature space belongs to that majority class or the dominant class. So that represents, essentially, you go to the limit of, in some sense, the null hypothesis. Right. So
Asif, you're not sharing the screen.
Excuse me. I'm sorry. Let me do that. Thank you for mentioning that. I am certainly getting absent-minded. All right. Is it any better? Yes. Right. Great. So the two approaches, nearest neighbor, when you apply to regression, you just pick a few points around it, and then you take its average. For classification, again, you take a few points, k points around it, and look at the majority. In both these situations, you realize that if you just look at k is equal to 1, you will have high variance errors, because if I had taken a different sample of data to learn from, the answer may have changed. By happen chance, you might have data points with more noise in it, and so your prediction would be off. So a basic smoothing method is to take sufficient number of points. Now, what is sufficient? What is good enough or a good number of points? That is the k, the hyperparameter in the model. You have to play around with it. By now, you must be realizing that machine learning, most of the algorithms are infested with hyperparameters. You have to not only train the parameters of the model if you have parameters, but you also have to then worry about the hyperparameters later on. In the neighborhood methods, generally, there isn't much training to do. It's a form of instance-based learning in which you just hold the instances of data in memory. And then when you have to make a prediction for a point in the feature space, you just find the k nearest neighbors, and you use that to make decision. So k is equal to 1 represents, in the bias variance trade-off, represents a situation of high variance, because it changes, like, it varies a lot. Which sample points you happen to have taken. On the other hand, when a k is very high, for example, asymptotically, when it is the number of data points itself, in the case of regression, it essentially amounts to the null hypothesis. Basically, you're saying the prediction at every point will be the average of all y values, right? Because k is n, all points are the neighbors, which doesn't help at all. And for the class of for classification, the same thing holds. The bigger the k, the more biased it becomes. The decision boundary becomes overtly simplistic, right? So that's a bias Bayes trade-off.
One question asked, this does not apply for high dimensions, correct?
Yeah, so we'll come to that. Let me just review in a moment. Huh? So now, the second question is, so you can say, well, that is bad. How do I mitigate the effects of the hyperparameter k, the change in the hyperparameter k? You know, just hunting for the best hyperparameter is a bit of a nuisance. You have to run it again and again. If there were some method that we need not have done that, we could have arbitrarily picked some k, and more or less the clustering, I mean, not the clustering, the regression and classification would be robust against small changes in the value of k. That would be good. And the intuition for that comes from the fact that if you find k neighbors, you would like to give a stronger voice or a stronger vote to the nearest neighbor, a lesser vote to the next nearest neighbor, and a lesser vote to the next nearest neighbor. So in other words, you want to take a weighted average, not just a plain average in which a far off point has, in the neighborhood, it still has as much voice or as much vote as the absolute nearest point to the point in the feature space you're looking at the point. So the way to do that is to, well, of course, apply weights. Those weights that you apply are called kernels, because to the kernel, we want to associate some well-defined properties. The kernels, these are called the distance kernels. Now, what are distance kernels? Distance kernels basically say that, in a way, how much a point influences the decision at a point. So suppose I have a point X and I have points A, B, C, D around it. How much A influences the decision at X should depend upon, should I draw it out perhaps? What we are saying is, suppose you have a point X. This is the point you want to make a prediction on. And let us say that you have points XA, XB, XC. Are you able to see my writing?
Yes.
Right, XC. And more than that, you have XD. And maybe I'll take XB a little bit further away. Right. So given this point, you realize that you can order it. The distance to XA, X, is less than distance to XC, X, and which is less than, actually, from this picture. If you look at it, it is less than, I'll draw these things out. This distance is longer than distance of X, B to X. Would you all agree? Which is less than the distance of X, D to X, right? So the order of distances is A, C, B, D from this picture. Let's look at these distances. Would you agree?
Yes.
Right. And so what you want to do is you want to have how much influence they have on the vote to be proportional to how far they have, inversely proportional in some sense. What you want is further points have less influence. So to capture that notion of influence, you need a function whose basic quality should be that in the very minimum, the influence shouldn't increase with distance. You would agree with that, isn't it? So you say that you need a function that is monotonically decreasing and continuous. Continuity is obvious. If you don't have continuity, then you have zones in which you simply can't find what influence points will have if they were there. So obviously, you do want a continuous function. So continuous is obvious. I hope decreasing makes sense, and monotonically means it has to slowly decrease. It cannot just suddenly go up and do like that, because there is no rhyme on reason. It doesn't agree with our intuition of what we are trying to say, that the further you are, the less influence you have. Right? So what are valid kernels? Well, a flat line, a flat amount of influence is also invariant of distance is also a valid kernel. Why? It is decreasing. Not at all, but it's certainly not increasing. A step function such that all points within a certain radius you consider to be of the same influence, but beyond that, you don't do it. So then you're essentially shining a torchlight around that point, isn't it? So suppose you do this. Let's look at this blue line. What is this blue? What is this blue line doing? It is creating a circle around it. So the blue line's kernel would be a step function, isn't it? Which is the radius. Let's say the radius here. When you go at a distance d is equal to the radius, what happens? You don't take any points beyond that. So therefore, the influence is 0 outside it. It's a step function. It's a step function, right? If you haven't encountered step functions before, just literally think of it as a step into your house. That's what it looks like, outside, inside. Then it could be a linearly decaying function, the yellow line. It could be the pink line, or it could be the light blue line. It could be anything, basically, so long as it fulfills the condition that's a monotonically decreasing continuous function. So far, so good, guys? And so what you do is that you take the values, the weighted average for regression and the weighted vote for classification. And these things, and today, in a way, we got introduced to this lovely notion of kernels, distance kernels. It turns out that distance kernels are a special class of kernels. Today, as we make progress, we will learn about kernel and kernel machines in a much more in-depth manner. In fact, we may not be able to finish the whole kernel stuff. Today, I'll introduce you just a touch of the main kernel machines theory, because it gets quite mathematical. It's a beautiful, beautiful mathematics, gets elegant, but it's usually not something I would cover in an introductory course. Usually the mathematical details we keep for the math of data science. That's where we do that. Right? But I'll introduce you enough to this theory of kernels. So that is that. Then
what are you dividing that by? What's the denominator? Sigma k?
Whatever the sum of weights. That's what you would do, right? The sum of weights.
Okay.
Just to normalize it. So suppose you want to take the weighted average. Let's say that you want to weigh something by 2 and 1. 2x1 plus x2. So what should your denominator be? 2 plus 3, right? Because what you want to say is 2/3 x1, 2/3 contribution should come from x1, 1/3 contribution should come from x2. Sorry, 2 plus 1. I take that back. 2 plus 1 is equal to 3. This is how weighted averages work, isn't it? Proportional.
So that's a constant, though, right?
That is a constant. That will be a constant. Yeah.
It will be like the number of points that we have taken.
No, not number of points. Remember, it's the kernels.
Correct. That's why I'm kind of.
See, okay, let's think about it. Given a point, x vector, let's say that around it are the points x1 all the way to xk. Right. So now at each of these points, you have xki. Right. So suppose you're trying to find the y value. So what will you do? At this point, you say that this guy, x1 is saying that the y should be yi, because that's what's the value of yi there. The second guy, so each of these guys is saying this, right? So now what happens? So total in now this k that is there. Suppose it was okay. For example, let me make it simpler. Suppose there were only 2 points, 2 nearest neighbors, right? This is x1, this is x2. So what will you do? You would say, and let's say that k x1 x and plus k x2 x, and this is of course y1 and this is y2. You do, but you realize that you cannot just add them up, because suppose each of these are, you need to scale it down. Right. You need to take proportional weight. So what you have to do is, so suppose this was equal to 2 and this k is equal to 1, right? This is equal to 2 and this is equal to 1. So basically what you're saying is this guy has twice the influence of this guy. And so the total influence that the collective they have is 3. So what you're really saying is that you need to divide it by 3, which is equal to 2 plus 1. Isn't it? What have you done? You have just said this is equal to summation of x, xi, kxi, sorry, a summation of k of xi. That is what you just did, right?
So this will vary depending on the neighborhood points, like that.
K points, yeah, K
Right?
points.
That's what I'm trying to understand, right? That
Right.
It's not like a constant you can think of. It's
No,
wherever you are.
Yes, there it is.
Is going to change.
Is going to change, definitely, definitely. Both the numerator and the denominator will change. That is right. And but what it gives you is a more robust estimate at that point. It just agrees with common sense that nearer point should have a stronger influence or stronger voice, isn't it? So that is the notion of kernel. That's what we did. The second thing that we did, which was a slightly longer journey, one of you asked me to explain spectral clustering, which was a long intellectual journey. So we went into a digression and talked about eigenvalue decomposition, which I won't repeat today because we are going to do it when we do principal component analysis in detail. But basically, eigenvalue, just as numbers can be broken up into primes, matrices can be broken up into components, and there are many interesting decompositions of matrices. One of the very powerful decompositions is eigenvalue decomposition. And what it does is, if you take a matrix and apply it to a matrix which is like this, symmetric matrix like this, then you apply with certain conditions. If the matrix is in some sense well behaved, then it will transform a circle of points into an ellipse of points, and in higher dimensions, a sphere of points, hypersphere of points, into hyperellipsoid. And those ellipsoids will have major and minor axes and all sorts of different axes in them. And those axes are the direction of those axes are the eigenvectors, and the degree to which they are stretched out are the eigenvalues. Now, the way this spectral clustering worked is you look at the k nearest neighbors, for example, that's one approach, and then you create an adjacency matrix. Then you take a degree matrix. We have two different things. These are all coming from graph theory, and we'll do it in greater detail someday. Then it turns out that degree minus a, right, gives you something called the Laplacian matrix. Laplacian matrix has a lot of very nice qualities. It's sort of a key concept in graph theory. Now, given the Laplacian matrix, if you do the eigenvalue decomposition, and it will project it into a space where the eigenvalues have a exponentially decaying set of values, and you can throw away some of the directions where the eigen are small. And so what you're saying is those directions don't matter. And you can therefore only look at those, look at the subspace made up of eigenvectors, the first few eigenvectors. So you have taken data and projected it into a lower dimension space. Whether, guys, whatever I'm saying, if it doesn't resonate with you at this moment, hold on, because we'll do dimensionality reduction in great detail. But once you have done that, the long intellectual journey is you take those vectors, and then into that vector, you project every point. And once you have projected the point, you will you can then apply your k-means clustering or whatever favorite clustering algorithm that you want to apply. That is the whole story of the spectral clustering. So in simple terms, it differs, by the way. People ask, how is it different from principal component? In principal component analysis, you factor the covariance matrix. Here you factor the Laplacian matrix, which is a core entity in graph theory. So that's the difference. Right? Anybody here with a background in electronics and communication? So you should be remembering your spectral theorem. Right, and so pretty much these things are all in many ways related, but we won't get there. So today we are going to start now with a completely new topic. I'll give a 5 minutes break, then we'll start with support vector machines. Kyle, are we recording? Now we are going to start on a new topic. This topic is called kernel methods. And associated name with it is support vector machines, which are actually simple machines. But the kernel methods, the whole topic is large and it has a lot of implications. When it came out in the early 90s, it was supposed to be quite a revolution. And I have heard quite a few stories about how it all happened. I don't know how many of those are true and how many are not. Well, the breakthrough apparently was made by a brilliant person, Vladimir Vapnik, who made this breakthrough in the 1960s. It was way ahead of its time when he submitted it to the math department or the math journals. They all rejected it, apparently. Then he tried neuroscience journal, and apparently, from what I understand, even there it didn't get published. So it had to wait for many years, 30 years before in US, there was some sort of a competition. I think it was the handwriting recognition competition, MNIST or something like that. And where he submitted, or his friend encouraged him to submit the results of his algorithm. And it was remarkably better than anything done so far. And obviously today, Vladimir Vapnik is a distinguished professor at MIT and has been there for a very long time. And I heard this story. So this is part of the giving you an insight into how things are done in reality. When we look at some work in books today, when we look at kernel machines, kernel methods, it is so mathematically elegant and so absolutely powerful it feels, but things start slowly. And Patrick Winston, who an MIT professor who used to teach machine learning there for many years, he has passed away. He told the story in his lectures that Vladimir Vapnik discovered it over what he said, many cups of tea in a cold Russian winter. Apparently he had gone to, if I'm right, to a Dacha or some place in a remote area of Russia, cold, quite isolated. And there, every day he would slowly build up the thought process, because to get this thinking right, and I will take you on the same intellectual journey, and it's a breathtaking journey that takes us from a simple idea to the support vector machines. So do please pay attention. I would strongly encourage you, in case you are keeping an eye on your laptop for messages from work or from social side. Today, I would request you, because this is a slightly tough topic, to please not do that. Give your undivided attention to this topic. It's very important that you do that. So with all of those statements or background, let me start. We will start with the distance function. If you remember, we talked about something called the distance function. Do you remember that, guys? Okay. The distance function was distance from a decision boundary. Let's say that there is a decision, or between at this moment, not even a decision boundary, between a hyperplane.
We're not sharing us.
Oh, I stopped sharing. Okay, I apologize. No, I am sharing. Why is this not showing up? Is nobody able to see my screen?
No, I can see.
Sorry, yeah, I
Maybe
can
he
see it
has
now.
a speaker view or gallery or something.
Yes. So let's take this situation. You have, yes. Suppose you have a hyperplane like this, hyperplane. We realize that the definition of the hyperplane in the way that we studied it was that any point, the distance from the hyperplane of a point X is given as beta naught plus dot x vector. Do you remember this, guys? Right? As a dot product between these two. Now, these dots may sort of get, I will introduce a notation that I like, beta hat x. So when I write this notation, bracket notation, I mean exactly this, dot product. It's a synonym. I tend to write it like this, this sort of angle bracket notation, because when I'm studying my own code or my own notes or scribbled handwriting, it is much more clear to me that it is. So if this is the distance to the hyperplane, you would agree that the hyperplane is given by dx is equal to 0 would be the set of all points on the hyperplane, isn't it? Because points whose distance is 0 are points on the hyperplane. So far, am I making a simple statement? Sanjeev, are we clear with this? Right? And in fact, the definition of a hyperplane is the set of all points that fulfill this criteria. So we say that another way that we can define a hyperplane, and just putting it very simply, a hyperplane is a hyperplane is an affine hypersurface who affine hypersurface given by beta naught, which is dx beta x is equal to 0, right? Now, what does the word affine mean? Now, affine mean it doesn't necessarily go through the origin. There's no reason that there's no constraint that this hypersurface or this hyperplane goes through the origin. Are we together? Right? A decision boundary, remember your grapes and blueberries in terms of weight and the cherries. So the decision boundary, if you remember, is this. Does this go through the origin? No. So this is your this is a hyperplane of what degree? Degree 1, isn't it? So suppose your feature space, so some very basic thing. If the feature space is equal to r to the p, p dimensional, the p features. So your feature space will be approximately r to the p, right? And I mean, forgetting about categorical variables for simplicity for a moment, right? So they're all measurables. Would you agree with that? The Cartesian space Rp. In other words, suppose you have two features, like in this case, weight, size. Would you agree that the feature space is R2, plane? Right, real times real. Now generalize it to P features, so it is Rp. And then the thing is, what would be the dimensionality of the line? In two-dimensional, in R2, what is the dimensionality of the hyperplane or the decision boundary? R1 or just R, isn't it? One dimension less. Would you all agree?
n-1, yes.
Yes, n-. So in the same way, if the feature space is then the hyperplane is dimensionality is equal to R p minus 1, one less. In three-dimensional space, it will be a plane, like as a sheet of paper. Right? And we can generalize to higher dimensions. So this is the only mathematics at this moment I want you to remember, and just be familiar with my bracket notation. This, whenever I write this, I mean nothing but this is by definition. Now, why do I put a hat over beta?
It's a unit vector, right?
It's a unit vector. These are unit vectors, unit vector. And in which direction is this unit vector going? This unit vector is in a direction orthogonal. This is the unit vector, orthogonal to the plane or the line or the hyperplane, right? So it is the orthonormal vector. So we say a unit vector is orthonormal to the plane, beta hat. So we'll just, this is all a review of what we have done, is an orthonormal vector to the hyperplane, right? And so you realize, so this is the way that you posit this thing to be.